We're going to take a return to solitary waves now, and Viktoriya Yarushina presenting her talk today.
Thank you. This work has been done together with Yuri Podlachikov and Ludovic Ras from University of Lausanne in Switzerland, and Nina Simon from Norwegian Institute for Energy Technology. And I will talk about decompaction waves in porous viscoelastoplastic media and their implications for focused fluid flow. In this workshop, we heard quite a lot about melt transport in the deep earth. In my presentation, I will talk about more shallow examples of fluid flow which constrained to the crust. I will talk about the most shallow examples which come from a few hundred meters below the seabed. And after I will describe several examples and their importance for, in particular, industrial practice, I will talk about mathematical modeling of fluid, focused fluid flow. What can we learn from thermodynamics? What can we learn how we should drive closure relations, which is a non-trivial problem, as John already emphasized in his talk yesterday. How we can verify our equations experimentally, and finally, how to implement our equations numerically so that we can produce sensible results. So here is my first example and the deepest example. This example was imaged with seismic tomography underneath Mount Spur volcano in Alaska during fluid ascent in 2004-2005. What we can see in this image, red colors emphasize areas of high VPVS ratio, which indicate presence of fluids, and not just fluids. It was proven that these are actually liquids. This is a liquid phase that ascends upwards. So we clearly see two channels. One of these channels almost reaches 2 kilometers below the seafloor, and it's roughly 30 kilometers deep. And another channel is much deeper. The top reaches 20 kilometers below the seafloor, and the channel itself is around 20 kilometers deep. And this picture just shows cartoon interpretation by observers. So what they say is that there is definitely fluid ascent along these channels, which can be also directly observed at the surface as fumaroles. So what happens here is that liquid goes to the shallow depths, it decompresses, and it evaporates here. So they interpret this boundary as a moho and draw something like magmatic plume, which is actually not seen on seismic data. So the source of these channels remains invisible on seismic images. The most interesting picture or feature in this picture are these yellow dots, which are induced seismicity associated with this plume propagation. So the same pattern that focused fluid ascent and associated seismicity was observed in some other places. The same authors report similar type of data, seismic tomography and observed microseismic locations from Kamchatka, below one of the volcanoes. We also see evidence for focused fluid flow and associated seismicity from the work of Bob White, who was present here in this workshop. So the question is, what happens these channels, and what is the physical mechanism that would consistently explain channels and this seismicity in the same, at the same time? Another example is much shallow. here we see multi-channel seismic reflection profile across the North Barents Sea basin, and the whole profile is approximately 10 kilometers deep. So what we see here, this is already interpretation. All these colors, it's cartoonish type interpretation of seismic reflection data. So what we can see here are multiple vertical channels, which sometimes are linked to horizontal structures. So these channels we interpreted as dikes and cross-cutting seals. So these dikes are most probably related to emplacement of magma into sedimentary basin. Yet more shallow example comes from multiple observations of so-called seismic chimneys or gas pipes in sedimentary basins, and most often such features are found in actively producing hydrocarbon areas. So in this example we see some seabed chimneys. So these are areas of deteriorated seismic quality. So they actually represent areas of high attenuation of P waves. Such features quite often can be traced up to the sea floor, where they break into pop marks or some circular craters. So this is a map view. This is actually the area where these particular chimneys come from. This is Norway. This is Norwegian Sea. So this is mid-Norway, let's say. And Niega area is area where a lot of hydrocarbon fields, actively producing hydrocarbon fields, are located. And this is again map view of this area, a little bit with magnification, and these circles indicate how these chimneys look like on the surface. So you see that on the surface these chimneys break into very circular, sometimes slightly elliptical craters. Depths of such chimneys can vary from a few kilometers to few hundred of meters. An interesting feature about them that with all the effort, it's very rarely people can trace them down to reservoirs or see any sort of feeder or chamber with fluid underneath them. Although in some cases we know that yes, there is a hydrocarbon reservoir somewhere down there, but there is still a very considerable distance between the chimney channel and the reservoir. So how the fluid goes there, how these chimneys are formed. Formation of such chimneys, by the way, continues nowadays, so these are not relict structures. We know for sure that these chimneys appear from time to time, and their formation is quite fast. We even observe that such chimneys, they are somehow related to industrial practice, which I will show on next slide. So here's a little bit of locations of such chimneys, so where they observe. So is it actually something unique maybe for Norwegian Sea? And these circles show the locations or reported locations of these seismic chimneys, also in Barents Sea. But also such chimneys were reported for the Gulf of Mexico. It was reported for offshore Nigeria, Namibia, even in South Korea, and in many other places all over the world. What is most importantly why we at Institute for Energy Technology, where we're supposed to care about energy and industry, are concerned with focused fluid flow and these chimneys. This is a simple example from Sleipnir CO2 storage site. And as many of you know, Sleipnir pilot is one of the world's first pilots, most documented. The CO2 injection there runs already for more than 20 years. And Statoil, who is an operator of this site, is very careful. They take quite a lot of measurements. They run quite regular seismic surveys. So we have quite a lot of data about that site. And here is a compilation map of a Sleipnir area. So this yellow area is actual location of the CO2 plume. And dots here, red, green, and gray, indicate observed seismic chimneys. So you see they are all over the place. And here is one of the seismic profiles across Utsira formation where CO2 is stored. So this is the CO2 plume. So what we see is that there are quite a lot of big seismic chimneys adjacent to this formation, but also we can see seismic chimneys within the CO2 plume.
Sorry, just clarification. When you say plume, that's the storage area, not actually something that's leaking.
Well, leakage is a controversial issue, so of course the operator claims that there is no leakage. So this is actual plume.
Okay, sorry.
Yes. So the questions here are, first, chimney flow and CCS. Are chimneys represent potential CO2 leakage mechanism? So this is something that we want to know. So those chimneys that we do observe on seismic images, is it a bell that rings to us that be careful? This is one question. And the second question is, can shales be considered as a reliable seal? And the reason for this question actually is that feature of Sleipnir storage site. You know that it contains 9 layers of shale barriers. And usually people used to think that shales are impermeable. And yet CO2 injected and it managed to penetrate through all the 9 layers of impermeable shales. So how did it happen? So related to all of these examples is the question how to model fluid flow in porous rocks, and in particular fluid flow focusing. Is it a trivial matter? Well, we heard quite a lot about that, but still one more simple example. And this simple example comes from the very basics of porous theories. So this is probably one of the first porous theory, poroelasticity by Bio, which was formulated in 1941, even before our two-phase viscous models were born. So Bio formulated his theory of poroelasticity, which became quite popular among reservoir engineers, but researchers still felt quite motivated to work on this subject, and they re-derived these equations, they used new methods, and finally the group of researchers, which call themselves True Porous Media Theory, after doing lengthy thermodynamical derivations and a lot more mathematics than we saw before, they concluded that Bio theory is actually an ad hoc approach which doesn't consider the main principles of continuum mechanics. So this is a sentence from the book of the Boer, Trends in Continuum Mechanics of Porous Media. Well, this is a very strong statement. So what are the objections towards Bio theory? Here are 5 question marks taken from the paper of Wilmansky about Bio theory. So he writes, first objection, what is the coupling of stresses described by the material parameter Q admissible from the thermodynamic point of view? Next objection, is the contribution of relative accelerations admissible from the point of view of material objectivity? How are changes of porosity described by Bio's model? How should one write in the mathematically correct form the frequency-dependent permeability? And can one extend in a consistent way Bio's model to large deformation of the skeleton and other nonlinear effects? And this is exactly what we want, actually. It's this last point. If we want to talk about shallow earth and industrial applications, then suddenly elastic processes become quite important. And on top of pora viscosity that we heard before, we need to add elasticity. So before we proceed to deriving any equations, we actually have to find answers to all these questions, so that we will not be accused being an ad hoc approach. So I will focus a little bit more on the first critiques, which states that coefficients in Biot theory are not really thermodynamically consistent. So what this coefficient is about? You know, Biot theory, in the same way as in porous viscosity, you can decompose shear deformation, deviatoric deformation, and bulk deformation. So deviatoric deformation is fine from the point of view of everybody, but trouble comes when we talk about volumetric response. And volumetric response can be described as volumetric deformation of the porous skeleton and related pressure. So this is poroelastic version of just bulk stress-strain relation. So this is effective stress law, which tells that bulk deformation can be described in the same way as usual linear elasticity, given that pressure, usual pressure in the linear elasticity, where it's just one pressure, is substituted with effective pressure. And effective pressure is total pressure minus some coefficient, which is called Beer-Willis parameter, and fluid pressure. So this coefficient might depend on porosity, it might depend on pressure, it might depend on something else. So this is basically a nonlinear parameter. So in the true porous media, they also, after all the linearizations and after all the simplifications that they had to do with their series, they also derived effective stress law, which looks pretty similar, but not quite. The difference is actually in this coefficient. In Biot theory is this teeny tiny Beer-Willis parameter, which is 1 minus drain bulk modulus divided by solid bulk modulus. So it's a very well-defined quantity. While in the true porous media, this is a quite complicated aggregate. So in case of incompressible constituents, where our key solid approaches infinity, these two formulations are equivalent. But the trouble comes when we have compressible grains, compressible constituent, and we definitely, this limit is quite important. So the question is who is right and how to avoid mistakes. So obviously one of the two series has a mistake there. So how to avoid mistakes? Well, those equations, by the way, were derived under the same assumptions. So you cannot find discrepancies that, oh, okay, they didn't account for, let's say, for heterogeneity, or that they didn't account for some nonlinear effects, or for something else. So it's under the same basic assumptions of material homogeneity, linearity, and things like that. So ideally, it has to be the same result. It's a linear limit. So we start derivations of our poro-viscoelastic media. Started with the concept of superimposed continua, so we use the same mixture theory as Dave showed us, the same mixture theory as John Wright showed to us yesterday. So we use this approach to derive our governing equations, and we use micromechanical approach or effective media theory to obtain closure relations, to obtain rheology and material parameters. So the recipes of irreversible thermodynamics tell us that in order to write governing equations for multi-phase system, we have to write balance equations for each phase, which would include mass balance, momentum balance, entropy, energy. And these balance equations basically tell us that changes in all of these quantities, mass, momentum, entropy, and energy, are due to advection, due to fluxes, and due to sources. In a closed system, some of these sources should be zero. So the force with which solid acts on the fluid should be the opposite to the force which acts from fluid to solid. Plus, we have to add to these equations local equilibrium hypothesis, which we choose to formulate for each phase. And what we include in this local equilibrium hypothesis is the gravitational force, entropy, volumetric deformation, shear deformation. Here we have only equilibrium deformation, which is part of thermodynamics, plus we have compaction. And after some, so these equations have to be combined, and another restriction that we have from thermodynamics is negativity of entropy production. So whatever we choose for these forces, and these forces like this QV here is, for instance, this added mass effect, or this can be this Darcy drag, or whatever other force that have been discussed yesterday and today. This source here, it could be a melting reaction, or it could be dissolution reaction, or any other reaction. So we have to write system of equations in such a way that we assure non-negativity of entropy production, and thus fulfillment of the second law of thermodynamics. So we did this exercise, and of course no surprise that our mass balance equations look pretty standard. Force balance equation and Darcy law also look pretty standard, so we just recovered them. Nothing else, but we know what all this means, and the question that remains is how to write rheology. How can one extend in a consistent way Biott's model to account for large deformations, this is what we want, and nonlinear effects. So we want our rheology to be not just viscoelastic, viscoelastoplastic. So what we know about general rheology of any material? So there are three different types of rheology. Elastic, which is reversible and rate independent, and there are two different types of irreversible deformation, which is plastic and viscous. Plastic is instantaneous or rate independent deformation. It's like friction. And viscous is rate dependent. So viscous materials, it's something like honey. You put a spoon into the honey and it sinks with time, even though load doesn't increase. While plastic materials is something more close to plasticine. So you press on it, it deforms, you remove your finger, nothing happens. So how should this rheology look like in porous rocks? So here is some insight from experiments. What do we know about experimental rheology or experimental deformation of the rocks? Here is an example from sandstone and shale. Here is a measurement of permeability as a function of effective confining pressure. The same for shale. And porosity is a function of effective confining pressure. So what we see here, first of all, that these curves are nonlinear. So strain curve is nonlinear. First message. Second message, it's permanent. We remove our stresses, we unload our sample, and we see irreversible deformation. This curve didn't come back to the initial point. This is another set of experiments taken from Bao et al. On triaxial testing of sandstones. And this particular example is from Berea sandstone, but they have much more experiments like that. So what it shows to us that when we have isotropic stresses and we compact, then material goes like that. So it's a nonlinear behavior. It somewhat linear in between, but when we reach certain critical stress, we have sudden increase in the strain, which corresponds to transition from elastic type of behavior to elastoplastic type of behavior. So they call this as a pore collapse pressure. But what is also interesting that porous rocks somehow feel the state of the stress, whether it's just a hydrostatic compression, equal compression from all the sides, or whether we have some shear stress, which means that our axial load is not equal to our confining pressure. Then we observe so-called shear-enhanced compaction, which means that our compaction will be much stronger in the presence of shear stresses. This is also a quite interesting feature, which we will try to explain. Another set of experiments. Now these experiments are on time-dependent response, and rocks are all the same: sandstone, shale, and limestone. So this picture shows results of undrained laboratory tests under constant isotropic stress conditions, where bulk viscosity was estimated as a function of fluid and total pressure. So this is unpublished yet result, which was submitted to journal to GRL by Makhtenko and Podlatchikov. And here our in-house experiments on permeability of shales. Since we were involved in CO2 related projects, so our interest was to measure what is permeability of shale, what should we plug in into our models. And what we did, we put sample into the box and squeezed it from all the sides isotropically, and we looked at how permeability changes. Then we unload and we see that there is a permanent effect. We load again, permeability reduces again. But then at this point what happened, that experiment was interrupted. And nothing happened, but the specimen was still there. Oops. So what we found coming after several days is that permeability changed. Our permeability actually increased or reduced. So this clearly, and this is under the same load. So clearly, even in the permeability, you can see time-dependent response to it, which means you do observe creep in the experiment.
It eventually reduced or increased. So which one is next in time?
Decreases, because this is minus power. So you squeeze and you decrease your permeability. So the data shows that behavior of rocks on a short time scale is elastoplastic, and when we have we're interested in the long-term behavior, we have to consider viscous properties, even for sedimentary rocks, typical reservoir rocks. And closure relations, we show that closure relations can be, in a very general form, can be written if we use Darcy's flux, volumetric strain rate, and porosity. And we use total pressure and fluid pressure as stress parameters. The form of this equation follows from thermodynamics and assumption on matrix homogeneity. Yes?
Is Q the Darcy flux, or is Bragg Q?
This is Darcy flux, KD. And this is volumetric deformations, divergence of velocity. So this is the parameter which Mark Spiegelman uses and Dave, or its incremental version. So the form of these equations, let's say this is an exact result that doesn't depend on the assumptions on pore geometry. So the assumptions here is that our matrix is homogeneous, that we have porosity in this matrix, which doesn't even have to be connected. Our equations reproduce Bio's poroelasticity in the linear elastic limit, and notice, by the way, that here we have a nonlinear set of equations. So we formulate our equations in the rate form, so which means that they are valid for large deformations as well. So here we have Darcy flux related to pressure rate for elastic deformation and pressures for viscous deformation. And here we have volumetric strain rate, which is related to pressure rates for elastic case and pressures for viscous case. We also were able to reproduce with these equations exact Gassman's relations and Terzaghi effective stress law, which are two exact results in the theory of poroelasticity. So whatever you do, those must remain valid under assumptions made. And again, this is matrix homogeneity, so we have only one component composing our matrix. And the reason why we like this form of equations, we saw today and yesterday different forms, different decompositions of pressures, different variables that were chosen for calculations. The reason for this particular choice is the symmetry of these equations. So you can see that coefficients here in dp for Darcy flux, coefficient in front of dp total dt and coefficient in front of dp fluid dt in volumetric strain rate equation, they are equal to each other. So if you write these equations in the matrix form, our matrix possesses symmetry, which has a certain computational advantage. So it allows us to write stable numerical schemes. Yes?
Just issued the first two equations are actually mass balance equations, right? They are not Darcy. You are not giving Darcy's law here.
These are not mass balance. This is rheology. So this is poroelasticity. This is poroviscosity.
So you still need Darcy's equation, Darcy's law?
We will have to write Darcy equation on top of this.
And then you also combine it with mass balance?
Yes.
Sorry to interrupt while this is up. If I knew the first equation, could I get the second equation knowing conservation of total mass?
These two equations, they are independent. These equations would be the same in case of incompressible constituents like you have in poroviscous theory. And you can see that indeed, if you don't have this poroelastic component, then indeed these two terms are the same, and a gradient of the Darcy flux is the opposite to the gradient. For compressible media, you do have to write two equations. And the reason is very simple. If we think in terms of densities, we need to write state equation for density of the fluid. We need to write state equation for the density of the solid. Plus, somehow, we have to write porosity dynamics. So, three minimum equations. If you have incompressible solid, incompressible fluid, then we are fine just with one equation, which is porosity equation, and that is exactly compaction equations that we have in poroviscosity. So here, two equations on top, just because our material is compressible, elastically compressible. So our viscous limit is exactly the same as Dan Mackenzie has or Mark Spiegelman. Yeah, so or the Berkovici, let's say, without surface tension.
Basically, it is a modification of Darcy with respect to new rheology.
This is not Darcy yet, so this is just rheology.
But it is flux part of Darcy, yes?
Just a second. So here are the equations that I have to write on top of rheology. So those three equations is what had to be here. So those three equations plus mass balance, force balance, and Darcy law form the closed system of equations. So Darcy law, it just tells us how the flow through the matrix goes, but not how the matrix got squeezed, or not how fluid is squeezed in this matrix. when we apply the forces. Yes, Mark?
Go to the next slide again. No, I guess I get a little confused then. When I think of rheology, it's relations between strain rates and stress. And these.
So this is the strain rate, let's say, and stress.
Yeah, like it's the second one for sure. That's the strain. That's the volumetric strain rate of the solid phase.
Yes.
Right. So you could write a volume. You could do
Yes.
same. So. But
This
the last one, writing is d phi dt. That's.
Well, d phi dt, why we have to write d phi dt is just because all our parameters, they depend on porosity, so we need an update for porosity.
But that should come out of the
It just comes out
conservation of mass.
that, yeah, you've got the.
Yes, this is definitely not an independent equation, yes.
Okay.
Yeah.
But it just have to have explicit expression for porosity just because all our parameters depend on porosity. So we need an
Okay, so it's not
explicit
that's not a
update.
rheology per se. That's a
It's
combination.
just mass conservation.
So this
Yeah.
constitutive.
It's a matter of perspective, what you consider first, rheology or mass conservation. So for sure they... in fact, this equation is its form is somehow dictated by non-equilibrium thermodynamics. This is what you get, or at least this part. This is what you get from non-negativity of entropy production. And then what you also get from thermodynamics derivation, that stress to which your porosity has to be related, because it's also a question, what should porosity feel? Total pressure, fluid pressure, and like in this community it's pretty clear that it has to be difference between P solid and P fluid, or difference between P total or P fluid. It's quite similar. But in many communities it's still not a trivial issue, and I've got paper for review recently which says that porosity changes because of fluid pressure, and I make a comment, well, you have to be careful, porosity changes because of effective pressure, or P solid minus P fluid. And amazingly, authors started to argue with me that this is not correct. That there are cases when, well, it's still a not very trivial issue, as I said, and thermodynamics tells us that it has to be a difference between P solid and P fluid, or between P total and P fluid. Yes.
One question. So are you adding equation of a state? It is as well? Is rho of fluid a function of
No, it's already
temperature and other things?
inside here.
So where is temperature, for example?
We have isothermal process, so our temperature is constant.
And if it is not, would that easily come in here? Or would
Yes,
that be
yes,
very
it would.
different?
Yeah, it would be as usually we have the thermal deformation somewhere. Plus, all our parameters will have to depend on temperature. Plus, we would have to care about energy balance. Notice that I don't talk here about energy balance because I assume temperature is constant. Okay.
How does plasticity enter in here?
What?
In the previous slides, you say porous-elastoplastic, but where does plasticity?
Plasticity is in this module. So plasticity, by plasticity we mean micro-scale plasticity on a small scale, which after averaging actually leads effectively to nonlinear elasticity. And that I will show on next slide. So going back to this Biot-de Boer discrepancy, who is right and who is correct. Now, after done all these exercises, we can see that bulk moduli, or these material parameters, are the key to the puzzle. And what bulk moduli we have in the poroviscous media, which has incompressible solid grains and incompressible fluid. It's just bulk viscosity, it's just one parameter. But you can easily imagine that when we have compressible solid grains and compressible fluid, we should have at least two more compressibilities for bulk moduli. And there are quite a lot of bulk moduli that were introduced in theory of poroelasticity, and these are dry bulk modulus of porous skeleton, bulk modulus of the solid, and Yet another one is bulk modulus of pore space. So this is an equivalent of effective viscosity. And this is just compressibility of solid grains, which we don't have in viscous case because those are incompressible. So this would be just 0 for our poroviscous model. And this dry bulk modulus somehow feels not only compressibility of the pore space, but also of the solid. So there is a definite relation between the 3 parameters, which is shown here. So these are not independent. So, but the main message is there are several bulk moduli in poroelastic material, and when you interpret different series, you have to be careful that you compare exactly the same moduli in one theory and in another theory. So we will try to understand how to translate notations from true porous media theory into Bio's formulation. Well, this KSR module was interpreted by authors as compression modulus of the real material. So this is without any mistakes, definitely our solid bulk modulus, Ks. Another material parameter, which is this Ksn, was interpreted as compression modulus of the solid skeleton. And authors interpreted it as a drained bulk modulus. But is it so? Because as I already mentioned, there are several bulk modulus. And at least one more modulus can be candidate here, which is bulk modulus of the pore space. And to check this hypothesis, we just have a look at the definition of this bulk modulus from true porous media theory. So how it's defined is modulus between difference P fluid minus P solid and this E, which is deformation called volumetric strain due to change of pores in size. So this definitely something which is more like defy changes in porosity. So in fact, this modulus is a modulus between P fluid minus P solid and changes in porosity. So it's not a drained bulk modulus. In fact, this is just the bulk modulus of pore space. It's another modulus. And if you make this correction, then all the pieces of the puzzle fall into place. The two sets of equations become identical. So everybody is correct. So equations from Bio theory and from true porous media are identical, but interpretation of modeling by true porous media was wrong. And you laugh, but by the way, at least 2 or 3 papers were published with a question mark. Bio de Boer discrepancy, who is right? 3 papers without answer, just with a question mark. And this is a ridiculously simple answer. So luckily we will not make similar mistakes, and now we go further to the definition of our material parameters. Now that we understand what they mean actually. So two important material parameters that or basic material parameters that we have are elastic bulk modulus and effective viscosity. All other parameters can be derived from those using just usual translation tables or relation equations between drained bulk moduli, solid bulk moduli, and bulk moduli of the pore space. So the approach, as I already mentioned, that we choose here is effective media theory. But the question is how to choose representative volume element, how to prescribe the boundary conditions, and how to relate micro to macro properties. And this is especially important because we want to consider nonlinear response, which would cover not only elastic properties but also plastic, elastoplasticity, and viscoplasticity acting in parallel. And here again an example from literature. This is a summary plot of various bulk viscosities in the literature. So here you might recognize equations given by Stevenson and Scott, Sumita. These are two our equations from Takei and Katz, from Arts et al., Spiegelman et al., and from Mackenzie. And you see there is a quite difference. And of course you can always say that the difference can be attributed to different assumptions on pore geometry, which is true, of course.
Just made mine up, just for full clarification.
Well, you see that this, these lines, they go pretty close to each other, and those reflect more or less spheres. So models based on sphere approximation. These curves use different approximations, and so here we have this contiguity model from Takei and Katz, and our model with assumption of that pores are elliptical. So in a way, these curves more suitable for cracks or elongated pores. So indeed, some of the difference can be attributed to geometry. But we have also some opposite trends. All the viscosities, they go down with increased porosity, while some of them go up. So this is a little bit bigger issue, I would say. So we want to derive effective moduli. So that was again just a test case. We want to have some reference case to which we can compare our results afterwards. And we want to have those reference cases to be clear and fully understood. So we consider our porous rock as assembly of pores, cylindrical or spherical pores, which surrounded by shells. So if we cut our materials like that as polyhedrons and approximate them with circles, that's what approximately we get. Then the question, what should we prescribe on the boundaries? And the truth is that we have to prescribe total pressure at the external boundary of our representative volume element and fluid pressure on the internal boundary. And again, this is not really an intuitive answer at first. And there are also examples when people did prescribe different quantities here, and they got different results.
How defined in this is total pressure?
Total pressure is volume average of pressure within fluid phase and solid phase. So now we can use analytical solutions to obtain deformation and stress field within this shell and to average it. And in case when we want to add plasticity, we have to consider plastic response of this material. So if our stresses are low, then our shell deforms in a viscous manner or elastic manner. But if our stresses are high enough, then we have damage zone or plastic zone radiating from our inclusion, from our pore. And here are just some pictures, SEM pictures supporting this model. This is the pore or in the limestone, and you can see clearly a halo of damage around what seemed to be cylindrical pore or maybe spherical pore. And we assume that plasticity on the pore scale is driven by three different, this is Griffith's criterion, is driven by Griffith's criterion, which we approximate with three linear simplified functions. This is pressure insensitive yield given by von Mises standard criterion. This is dilatant brittle failure, which is described by Moore-Coulomb failure. And this is microfracturing, which is just a closing cup on the Griffith criterion. So we treat each of these cases separately, but we need this linearization to get analytical results, because elastoplastic or viscoplastic solutions, they are difficult already by themselves, without adding extra nonlinearity. So what we get from averaging procedures, and here I will stop on case of viscosity and viscoplasticity. Elastoplasticity will be pretty similar. So there is a certain correspondence between viscous and elastic cases. So in case when viscous deformation and plastic flow act in parallel, the difference that it adds to our porosity equation, to our compaction equation, is dependence of effective bulk modulus on effective pressure. So our bulk modulus not only a function of porosity, which we saw on the previous slide with all these curves of effective viscosity, but also of the pressure. And here we can see how this dependence on effective pressure look like. So under small effective pressure, which is below the yield stress, our effective viscosity is just constant. It depends only on porosity. But when we reach some threshold value, our viscosity is reduced and significantly reduced. And this means if we think about stress-strain rate curve, which is here, volumetric strain rate versus stress, this means that our stress-strain curve is nonlinear. It becomes, so our strain rate doesn't grow as much at high strains, at high pressures as for viscous material. And interestingly, that we have analytical expression for these curves, which I just didn't put here not to throw all the mathematics onto you, but this derived viscoplastic rheology of porous rocks is in fact an exponential creep, which is often reported for melts, in particular by Sean Carato. Here is example with more Coulomb plasticity, when our yield criteria is better described by more Coulomb plasticity. And this happens at much lower effective pressures. So what we see, this is again pressure strain curve, that our stress strain curve exhibits difference in behavior to decompaction and compaction. This is what Connolly and Podlachikov call decompaction weakening. So we do have difference in rock response to compaction, decompaction, and here is effective viscosity again as a function of pressure. During decompaction, our viscosity drops very significantly, while for compaction, yes, it drops, but much slower. And this rheological asymmetry was quite a big deal, around which Connolly and Podlachikov developed their porosity waves with elongated channels. And this is an example of how our rheology should look like in the case when we have combined pressure and shear stress. So now we have simultaneously compression and shearing. So interesting here is that our compaction relation feels not only pressure, but it also feels changes in the shear stress. And the shear stress, it enters, first of all, effective bulk modulus and effective viscosity, but it also a term in itself. So changes in shear stress can produce changes in porosity without changes in pressure. And this is an experimental fact. And here again, how effective viscosity looks like as a function of pressure at different, this is bulk modulus and viscosity, at different values of shear stress. So shear stress tends, increasing shear stress tends to reduce effective viscosity. And we can, based on our small microscale models, we can also construct this failure envelope. This would reproduce more Coulomb Griffiths criteria, which we have, full pore collapse, which is captured by the model. We can also tell what would be the area of purely elastic or purely viscous deformation. where we can expect homogeneous plastic compaction, or where we can expect localization of deformation, where we can expect areas of high strain rate, and even the compaction dilation line of
The total pressure and Q.
this is effective pressure and this is a shear stress. PQ are just notations that are most often used by experimentalists, so therefore they are used here. And
I have a quick question.
yes,
So you've only talked about how plasticity modifies the bulk viscosity or effective viscosity, but obviously the yield criterion is also a limit to shear stress, therefore it should also modify shear viscosity. Do you use something standard there, or?
for shear viscosity we didn't derive any expressions, so what we use for shear viscosity is just dependence on shear stress, standard equations for now. So this is comparison of our theoretical results with experimental models or with experimental data. The data that we take are from a triaxial test where we have cylindrical sample which is squeezed along the major axis of symmetry and compressed from circumferentially. So this leads to the following stress state. So this is two-dimensional stress state when we have axial stress which is sigma 1 greater than sigma 2, sigma 3 principal stresses in the horizontal plane. And these dots represent experimental data. Red curve is for hydrostatic case when confining pressure is the same as axial pressure is the same as confining pressure. And colored dots represent a different degree of shearing when stresses here are not equal. And as I told, dots are experimental data and the curve is our fit. So this curve was fit with just elastoplastic compaction relation based on von Mises yield criterion. And yeah, this is our model for shear enhanced compactions that you saw on the previous slide. Fitting parameters here. We always have a suspicion when theoreticians show fitting that there must be fitting parameters. So indeed, we have fitting parameters, and these are yield modulus, which is supposed to be yield modulus of solid grains, and shear modulus. So this how they look like for the case of limestone, and this is another example for triaxial test on tuff. And tuff is slightly tougher case. And the reason is because it's 32% of porosity. So theoretically, our models with single sphere should not work on it. Because there, everybody from homogenization theory would say, yeah, but we have interaction between the pores and things like that. And yet, the simple model of cylindrical pore, we just take essential physics into account. And essential physics here, I mean elastic and plastic pore collapse around the pore, able to capture the behavior of experimental curves. Yes, we have a slight disagreement here, but still the general trend reproduced pretty well. And this curve exhibits quite extensive hardening phase. So we had to include a linear hardening into our plasticity model. But linear, yeah, I'm finishing. But linear hardening is just the simplest. And these equations were implemented into numerical code. So Yuri and Ludovic did quite considerable work on it. So this is a high performance code with multiple GPUs with a lot of numerical advanced technologies. And this is an example of run with 240, and 968 points. So this is quite high resolution, and you can see how channels are formed from initial random distribution of porosity in porous media. The only external forces that we have here is the gravity force. And interesting, so this is the porosity profile. These channels represent high porosity. This is permeability plot, which shows that within the channel, our permeability increases 2 orders of magnitude, at least.
Sorry, are you using just standard power law for the permeability for us?
Yes.
Viscoelasticity only?
Yes. And here is the second shear stress invariant. So what is interesting here is that on top of these channels, we see quite considerable shear stresses. Remember the picture with microseismicity that I showed you, channels and microseismicity on top. I'll come back to it, and here I just cannot resist but show you this. Yes. So here you see formation of such channels from initial random distribution of porosity, so they rise and propagate upwards. And the speed of these channels, which is a very important parameter. So here we plugged in all the parameters for shale rheology, because we were mostly focused on CO2 sequestration example and those channels on seismic image from Sleipner storage site. So we plugged in shale rheology, and what we see that we got these channels propagating in shale with a speed of 2 meters a year. When we showed this presentation in Cell this autumn, they were representatives from Statoil who monitor the storage site, and they came to us and said, well, again, what is the speed of propagation of your waste? Well, you know, this is exactly what we observe. So we, without tuning of parameters, we actually did manage to reproduce the right, let's say, at least order of magnitude. And here is one of the latest runs. Here is a homogeneous material parameters, therefore, or homogeneous porosity. So therefore, we see only one channel propagating upwards. But what is cool about this picture is the resolution. It's 780 by 780 by 2,300 points. So most powerful computational facilities in Switzerland were overheated during this run.
You need to burn some fossil fuels.
Yes, to save the planet, yes, you still need to burn some.
So that's the one where decompaction is easier
Yes,
than
yes,
compaction.
yes.
It must be sucking in fluid.
Yeah, it's with decompaction weakening. And here is just some scales to our porosity waves, how fast they propagate. So 2 meters a year, as I told, in shale, and 100 meters a year in sandstone rheology. So this is what we can expect for our sedimentary rocks. So this is pretty fast. And you know, there are also, and this is also one of my favorite slides. You know, seismic chimneys, they're usually considered to be hazards. So people don't drill through them, people don't put installations onto them, they don't put platforms onto seismic chimneys. But this is somehow an exception. So they did drill through one of such chimneys, maybe by accident, I don't know. And what they did, they measured pressure within the chimney. And this is the pressure profile within the chimney. And here is our theoretically predicted pressure profile within porosity wave. So to me, this looks at least qualitatively similar. So maybe porosity wave do have something to do with these chimneys. And
did the porosity waves form the chimneys? And if so,
yes,
the chimney is already there. Hasn't the porosity wave passed?
No, they were not there. In our calculations, we had just random distribution of porosity, just Brownian noise. And we see that porosity waves form and they go through, they do form chimney. And these chimneys, they close, yes, as it propagates, but still it takes considerable time before it closes. And actually, there are controlled experiments on CO2 injection. It's the so-called KICS project, where they injected CO2 into 800-meter depths below the seafloor. And they observed after several days of injection with seismic images, and they also had divers who observed the seafloor. So they started to see that gas bubbles come to the seafloor, and then with seismics they found chimneys. So somehow you inject into sediments, and it's not a plume that you get, it's chimneys. They published a paper, and then they come half a year later to the same site. They make again seismic imaging. Chimneys are gone. There are no chimneys anymore. So this is what we see in our pictures. And here is just going back to these microseismicity issues, again comparison of shear stress, where you can expect plasticity or seismicity on top of the chimney and locations. Yes, I'm done.
Great.
Yeah.
Right, I don't want to eat too much into the tea break, so very quick questions, please, for Toby.
Just a quick one. Have you or Ludovic also done simulations with melt and rock rheology, more to do with like a mantle or lithosphere?
Not yet.
So you don't know what, or could you predict from your analysis what scale that these magma fingers could have?
Well, we can't predict the same parameters as everybody else does. What is the compaction length and things like that.
Okay, good.
But it's not exactly the speed of propagation of the porosity wave.
Lovely calculation. Just curious, these things are so unstable. One wonders, I mean, how do you keep hydrocarbons, if these are going on, how do you keep anything in the earth, any fluid?
Well, first of all, of course, when you go closer to the surface, you will lose viscosity. And viscosity is a very essential parameter to drive porosity waves, as we know. So at some point, these porosity waves can be simply blocked. Or they can develop into hydraulic fractures and behave like fumaroles on top of that volcano.
I'm just thinking, you know, oil and gas and water that's trapped in the earth.
Yeah, but this is a known fact that there are these shallow reservoirs that actually escaped from deeper reservoirs. So yes, indeed, hydrocarbon leakage we do observe, and this is an issue for oil companies.
Very quickly.
So these chimneys that I see in the seismic images of sedimentary basins, they're not all active. A lot of them are very old.
Yes.
And it seems to me that in your model, once the wave has passed, then the chimney disappears. But the ones that they observe in the sedimentary basins, they don't disappear. Is that consistent with what you?
Yes. First of all, as I said, the important parameter that makes these chimneys disappear is viscosity. But in sedimentary basins, you might expect more significant elastic properties than viscous properties. So viscosity might be not that significant in comparison with elastic flow. So it brought initial pressure pulse to the surface, but then it changes to another mode of propagation.
Couldn't it be just real plasticity? You know, you're below, once it falls below the yield stress, say the same thing. Maybe
Yes.
elastoplastic at that
Yes.
level.
Right, I think I should really leave things there. We'll have some tea, and then we'll come back at 11:30 for the meeting.